All right, welcome back everyone. Our study of limits continues. I just narrowly escaped getting rained on while I was out to lunch. If you've lived in Florida long enough, you probably know what I'm talking about. So I'm glad I made it back safe and dry. For now, we're going to be talking about these 4 topics. So I'm going to review some more one-sided limit stuff, and then I'm going to go into infinite limits. So this is when the actual value of the limit is some type of infinity. Next, I'm going to discuss limit laws. So these are proper algebraic rules that you can use when you're dealing with limits. And then finally, I'm going to touch on the squeeze theorem, and we're going to go over an example using the squeeze theorem. Okay, but first, I would like to define the following piecewise function. So we're going to define f of x to be equal to x minus 1 when x is strictly less than 0, x squared when x is between 0 and 2. And then there's a third part to this piecewise function. It's going to be 6 minus x when x is at least 2. So just like with the other example from the last video, I'm going to draw a picture because these functions are easy enough to where I can do that. So let me start drawing my picture right here. And I need to think about 3 separate sections of this. So the first one is going to start at 0, and it's going to be on the left side. So if I plug in 0 into this top function, the top part of this piecewise function, I'll get -1. I'm going to put an open circle at that point because it's strictly less than. So I need an open circle. Then I know it's a line, and its slope is +1. So if I want +1 slope from here, I'm going to achieve this by going down 1 over 1, down 1 over 1. And then if I read this left to right, I'm truly increasing, just like the positive slope here wants me to. Okay, so that takes care of this piece right here. Next, I need the good old x squared graph, but I only want it from 0 to 2. So at 0, I'm going to include this because it's equal to, and it's 0 at 0. And I just need a piece on the right side of the graph. I'll plug in 2 just to get an accurate picture here. So if you plug in 2 to x squared, you get 4. And I know it's got this parabolic shape. Now, both of those are filled in circles because these are my equal to signs. And then this will be an open circle. And I'm going to start where I start here, which is 2. And if you plug in 2 to the bottom piece, it'll be 4. So I need an open circle at 2, 4. However, luckily I have a closed circle on there to cover it up already. And then I'm going to go -1 for my slope here. So this is going to be down 1 over 1, down 1 over 1. And this is the entire graph. So it's split up into these 3 pieces. Now I can easily evaluate limits. So that was my goal of drawing the picture. Let's try a couple limit problems. So what would be the limit as x goes to 0 on the right of f of x? Well, we need to focus at x equals 0. So at 0, if you're on the right side, if you didn't know anything else what's happening on the left side, I would say that this was about to go to 0. I noticed in my previous video it was kind of hard to see whether I wrote right or left, so I'm going to try to write these much bigger now in the videos. Next, let's go x approaches 0 on the left side of f of x. So here's 0 right here. If I'm on the left side, I'm over here. It looks like, without knowing the other side of the graph, this would approach -1. It looks like it's about to go to -1. So from these two, you should be able to tell me that the limit as x goes to 0 of f of x overall, because these two are not equal, is nothing. Does not exist. So does not exist. How about the limit as x goes to 2 of f of x? Just 2, not left or right side, just 2. So if we go over here to where 2 is, it's between these 2 functions. So if you look at 2, on the left side it goes up to a filled in 2. On the right side it goes up to a filled in 2. So they both approach here at 2, but then they come to 4 for the value. So at 2, it looks like we're going to reach the exact same spot. So that's 4. So this limit exists, and it's because the left and the right-hand limits are the same. How about we look a little more now at different types of limits? So I want to do an example of infinite limits. So I think with an example, you'll see what I mean of what's going on here. So we're going to let f of x be the tangent function, tangent of x. So hopefully you recall what this looks like. I'm going to draw a picture for you just in case you've forgotten. I do have this, and I think lecture video 2, there was our trig review. So you could go back and look how I drew this graph. I think I put it in there. This is equal to sine over cosine. So you're going to have spots, infinitely many of them, where this goes undefined. And you have to think, how do you make the denominator 0 here? Well, you can plug in pi over 2 for cosine. And if you do that, then that's a 0 in the denominator. Same with negative pi over 2. You could plug in negative pi over 2. And that would make the denominator 0 as well. And then tangent of 0 is just 0. This is the general shape. This is one period of tangent, and it just kind of repeats this picture over and over again with the same spacing, if you can imagine that. So there's another one over here, and there's another one right here. So I just drew this strip right here, but then we could just keep copying this, if that makes sense. All right, we can do limits with this one too. So let's look at the limit as x goes to pi over 2 on the left of f of x. So at pi over 2, I want to be on the left side of pi over 2. Right now I have this kind of wall that's happening at pi over 2. It's undefined here. This is called an asymptote. So this is called a vertical asymptote. So we have to be careful around here. So if we're on the left side of the wall, let's see what the function's doing. It's going up, but we're never really reaching a value, are we? We would go up forever. To signify that we're going up forever, I'm going to write infinity. So infinity means we go up forever, basically. I can never quite give you an L value because we just keep going to greater and greater values. So this will be infinity. And how about on the right side of f of x? So the limit as x goes to pi over 2 on the right side. So here's the wall again. If I'm on the right side of the graph, this would go down forever. So you can probably guess what this would be. This would be negative infinity. So the limit as x goes to pi over 2, just the general limit, without considering left or right sides, is, oh, not infinity. I wrote that too soon. I don't know why I just immediately wrote that. This would be what? These are different, right? The left and the right do not equal each other. So this does not exist. OK, so same idea. The graph really helps here if you know what the standard graph is for tangent. OK, let's give you another one to try. So how about the limit as x goes to 0 of 1 over x squared? One thing you could do is take numbers very, very close to 0, like we did in the previous lecture, and see what's happening. You could use a calculator and see what's happening to this function. For this, I'm going to use the graph this time, because I know what this graph looks like. If you didn't, you could plot a couple values, and then you probably would start to see the pattern. There is one value you're not allowed to plug into here. This one had many values you're not allowed to plug into it. But what is the one value you can't plug into that? Well, that is 0. You can't have 0 in the denominator. So here we'd have a vertical asymptote at x equals 0. That's a vertical line, and this is an asymptote. So the graph will not cross here. The general shape of this graph, to me, it kind of looks like a tree trunk. That's how I remember this. You can think of whatever you want to remember that, but that looks like a tree trunk to me. So it goes up like this. It's only on the top two quadrants because this squared will always keep this expression positive. So that's why it's up here. And the graph kind of goes like this, and it goes up forever, and it never quite gets to the wall here. There's an asymptote right here. So my question for you is, what is the limit as x goes to 0? Because that's the important, that's the thing we're testing here, is like what's happening at this weird point. What is the limit as x goes to 0 on the right of f of x? Well, here's 0. If we go on the right, we're going to go up forever. This is infinity. Similarly, if you were to go on the left side of 0, so from here, go up here forever, it's also infinity. So I'm going to say that because the left-hand limit and the right-hand limit are both infinite, the same sign, infinity, then that means that the limit as x goes to 0 of f of x is going to be infinity. Okay? So when you see these kind of infinite limits happen, like you approach some kind of value for x, and it goes to some kind of infinity, that's a signal that there's some kind of vertical asymptote happening in the graph, that it's coming up against a wall. So that's what's happening here. You're going to see this some more in later lectures, but it's good to show you now while we're talking about one-sided limits. All right, I'm going to stop there, and I'll see you in just a sec when I erase everything, okay? Welcome back. So now we're going to talk about limit laws. Whenever you get a new mathematical object, you want to know ahead of time what you are allowed and not allowed to do with that object. So these are going to give you the rules for what you can and can't do with limits. It's a little tedious because there are quite a few of them. However, don't panic. You don't have to memorize all of them or anything. Mostly when you're doing problems, you're going to get used to using these laws, and you're going to get a feel for what you can and can't do with limits. At the very least, I've seen maybe multiple choice questions that ask you which of the following might be a limit law, or which one is not a limit law, or which one's valid. So you want to have a working knowledge of what these are, but most of the time, I'm not going to personally ask you to list all the limit laws or something. I'm just going to ask you to use these in problems. So they're kind of in the background of all the problems you do. OK, with that being said, let's get started with them. So the first one I'm going to point out after I give you some assumptions. So we're going to suppose C is a constant, and we're going to say that the limit as x goes to a of f of x and the limit as x goes to a of g of x exist. So this is the scenario we're in. We have two functions, f and g, and we know ahead of time that their limits exist. So this is what we can do with that knowledge. So the first thing we can do is that we know that the limit as x goes to a of the functions added together or subtracted, so I'm going to put a plus or minus symbol here, is simply the limit of the first plus or minus whatever you started with the limit of the second. So you could think of this as like the limit is an operator that kind of distributes across functions. You can either add the functions first and then take the limit, or then take the limit of each function separately. They're the same thing. For 2, we're going to say the limit as x goes to a of a constant times a function is the same thing as just taking the limit and then multiplying by the constant when you're done. So to put this like in layman's terms, a constant will just factor out of the limit. So that's all that means right there. OK, our next property, property 3, is going to be that the limit as x goes to a of f of x times g of x is just the same thing as the product of the limits. It's the limit as x goes to a of f of x times the limit as x goes to a of g of x. So you can either multiply the functions first, do the limit, or you can just take the limit separately and multiply what you have. And you can probably expect what the last one is going to be here for this set. So the limit as x goes to a of a quotient f of x over g of x is, well, you can evaluate these separately. So you can do the limit as x goes to a of f of x, divide that answer by the limit as x goes to a of g of x, provided the limit as x goes to a of g of x is not equal to 0. So you cannot divide by 0. So as long as this limit is not 0, this is valid. You can do this. OK, that's my first group. I'm going to have another group of these shortly, but I want to break it apart with some examples because writing rules like this is very tedious for both you and me. So here we go. Let's do an example. We're going to suppose that the limit as x goes to 2 of f of x is 5. And we'll suppose that the limit as x goes to 2 of g of x is negative 1. So let's find the following. So find, for part A, we're going to do the limit as x goes to 2 of f of x plus 6g of x. So we're going to use a couple properties. First thing I'm going to do is I'm going to take this limit and I'm going to kind of distribute it in, because the first rule says I can do that. So I'm going to say that this is the same thing as the limit as x goes to 2 of f of x plus the limit as x goes to 2 of 6g of x. OK, so that's where I am so far. I'm switching my marker because I'm getting frustrated that this isn't showing up too well. So we'll try this one. The limit as x goes to 2 of f of x is given. That's 5. So this is 5 plus. A constant can be brought out front. That is my second rule over here. So this is equal to 6 times the limit as x goes to 2 of g of x. This is 5 plus 6. The limit as x goes to 2 of g of x is just negative 1. So if you take care of this, this is going to be negative 1. OK, so I use properties 1 and 2. When you get very comfortable with this stuff, you don't need to be as detailed as I'm being, especially when you're working with regular functions and not just functions that are named without an explicit formula. Let's try another one. Let's try this one. I'm just going to do the limit as x goes to 2 of f of x over g of x. So using rule 4, you can just say that that's the limit as x goes to 2 of f of x over the limit as x goes to 2 of g of x. And luckily, this is not 0. That's actually negative 1. So you're going to get 5, because that was given, over negative 1. So that's just negative 5. OK, and then my last example, I'm going to try to fit the example right here. I think I can do that. So here's my example. This is going to be the limit as x goes to 3 of x squared minus 4, x squared plus 5. I'm using property 3 here because here I have multiplication of two functions. You could think of this as a function and this as a function. So the way you split it up is you say it's the limit as x goes to 3 of the first one times, because this is multiply, times the limit as x goes to 3 of the second one. From here, I can go ahead and just evaluate these. So the limit of this is a continuous function. There's no problems on the domain, so I'm going to plug this in. and I'm going to get 9 minus 4 is 5. This one, I see that that's a little too low. This one right here, same thing. It's a polynomial. You can just go ahead and evaluate. So this one, this one's 9 minus 4, which is 5. This one, if I plug in 3, I'm going to get 9 plus 5, which is 14. So overall, if I plug in 3, I'm going to get 70. OK. I will be back in just a second, and we're going to do more of these limit laws, the last batch of them, and then some more examples. So see you soon. OK, welcome back. Here are a few more limit laws that I want you to be aware of. So this is limit laws continued. OK? I believe we left off at 5. If not, I'm going to seem very silly, but I think we're at 5. So the rule is the limit as x goes to a of f of x to the nth power is the same thing as, here in brackets, the limit as x goes to a of f of x to the nth power. And this is for n, a positive integer. So think like 1, 2, 3, ... Those types of numbers. So all this is saying is to take a limit where you have a function to a power, you could take the limit of the function first and then do the power as an afterthought. Here's the easiest one. So the limit as x goes to a of c is just c. So the limit of a constant is just a constant. So I'll even give you an example because this one's pretty quick. The limit as x goes to 10 of 100 is equal to 100. That's just because there's no x in the expression here. So you just get 100. It doesn't depend on x, so it's just going to stay 100. And then very similar in spirit to that one is this one. So the limit as x goes to a of x is just a. X is a very nicely defined function. It's just the diagonal line. So you just plug in a for x, and you get a. So we evaluate it. Next, for number 8, I'm going to say the limit as x goes to a of x to the n is just equal to a to the n. And this is, again, for n, a positive integer. So very similar to this one, you're just going to plug in a. X to the n is very well behaved for n, a positive integer. It's just a polynomial function. The last one I have for you today is this one. So the limit as x goes to a of the nth root of f of x, this is equal to the nth root of the limit of x to the a f of x. And this is for n. I'll talk about the n in a second, because there's a little bit of there's some restrictions that are in the background for this one that I want to explain a little more. What this is saying is if you have some kind of root, then you can bring the limit inside the root, take the limit of the function first, and then take the nth root when you're done. So first, n is a positive integer. So that's what I'm requiring for this property right here. Also, if n is even, assume that the limit as x goes to a of f of x is at least 0. So I'm doing this because if you have a square root, so say n is 2, that's the first even number I'm considering. If n is 2, it's a square root, or if n is 4, it's a fourth root. You can't take the square root or the fourth root or the sixth root of negative numbers. So you'd want to make sure that what's in here is at least 0. I'm going to even include this. So if it's an odd power, so if n was odd, then you don't have to worry about that, because you can take the third root or the fifth root of negative numbers. For example, the third root of -8, that's equal to -2. because negative 2 times negative 2 times negative 2 is negative 8. So you can do the cube root of positive and negative numbers, but you can't take the square root of negative numbers. So that's why we have this extra condition for this law. Okay, I would like to do a couple more examples now with you. So let's find some more limits. The first one is going to be the limit as x goes to 2 of x squared plus x minus 6 over x minus 2. The first thing you should try doing is simplifying as much as you can. So up here, this is a factoring that we can do. So this is x minus 3. Actually, it's x plus 3, x minus 2. And this is over x minus 2. So right away, I'm going to go ahead and remove the common factor. So the limit as x goes to 2 of x plus 3 is what I'm left with. Now I can just go ahead and evaluate, because that's one of our limit laws that we're, it's a combination of them, right? Because if I take this is the limit as x goes to 2 of x plus the limit as x goes to 2 of 3. So it's kind of a combination of things we've seen. Plus this is a very nicely defined function, so we can just plug in like we were doing in the last video. But the limit as x goes to 2 of x, you have that right here. You just plug it in. So this is going to be 2. The limit of a constant, that's your constant rule right here. That's just 3. So this is 5. And you can think about all these rules, but really in the background, you're gonna learn them all, and you're gonna just plug in this 2 and get 5. Let's try another example. How about the limit as x goes to infinity of 1 over x? So what would that be? What I need to consider is drawing a graph. If the function's simple enough, my strategy of drawing a graph has been working so far. So let's draw a graph. I drew for us 1 over x squared earlier, but 1 over x looks something like this. I don't really know what to tell you that looks like. It's not a tree trunk. It certainly is not a tree trunk. In the first quadrant, you have a piece that goes like this, and in the third quadrant, you have a piece that goes like this. So x approaching infinity is something I don't think I've written yet. What this means is that the x is going to go to the right forever. So the x is going to just become arbitrarily large. So you want to think, what's going to happen if I were to walk this way forever? I would probably leave the video, right? I'm not on the screen anymore, but I'm coming back. Okay, so if you went this way forever, you would get closer and closer, but never quite reach what number? For the y value, because the limit is a y value. You're getting closer and closer to 0. So this limit is 0. If you go this way forever, you're approaching, you would think that you would get to 0. You're never going to quite get there, because this has a horizontal asymptote. The reason for that is you're never going to make 1 over x 0 by plugging in a real number. Okay, so this one is 0. All right, my last one I want to share with you. Let's try this one. So here we have the limit as x goes to 7 of the square root of x plus 2 minus 3. So the square root is only over the x plus 2. This is all over x minus 7. I'm going to try to use a different color and like section this off so it's less confusing. I feel like that worked in the other video. Okay. What you could do is you could try plugging in 7, seeing if this works out. Unfortunately, it doesn't. If you plug in 7 here, you get 0 in the denominator. That happens a lot with these limit questions, so don't get discouraged. There was a rule we had earlier that said you can take the limit of the quotient if this isn't 0. Unfortunately, it is 0, right? So we have to try something else. We're going to do an algebraic manipulation. So whenever you see something where you have a radical expression in the numerator or denominator, you're going to multiply by the conjugate. And that's like an algebraic trick that helps you remove this radical here. So instead of radical x plus 2 minus 3, I'm going to multiply by radical x plus 2 plus 3. So all you've got to do is change the sign of what's in the middle of the radical and then the other term. You can't just do that to the numerator. You have to do that to the denominator as well. So we multiply that to the top and the bottom. For the denominator, don't worry about multiplying that out. Just leave it as it is. So this is going to be the limit as x goes to 7 of x minus 7 times the square root of x plus 2 plus 3. However, for the expression and its conjugate, you should multiply that out because something's going to cancel. So root x plus 2 times root x plus 2 is just x plus 2. This is because if you multiply a radical by itself, but they're both real numbers, you're just going to get what's in the radical. Here, you have the two middle terms cancel out. So look at this. You have the radical times plus 3, and then you have the radical times minus 3. So you can think of those two canceling out. That happens because you have a difference of squares. Then you do negative 3 times 3 for the last two, and you get minus 9. So this is equal to the limit as x goes to 7. If you simplify the numerator, you get x minus 7 over the same thing we had before. So this is x minus 7, the square root of x plus 2 plus 3. Now you'll see the numerator and denominator both have x minus 7. So you can cross that out. And thankfully now, nothing's going to go wrong when I plug in my 7. So if I go ahead and evaluate this, I have the limit up here is just 1. So I'm going to have 1 over, because the limit of a constant is just a constant. Plug in your 7 in the denominator. I'm going to get root 7 plus 2 plus 3. And then that's just going to be 1 over 6. OK. There's a few other types of tricky limit problems that we're going to do in class that involve other algebraic manipulations, lots involving like complex fractions and stuff. So we'll get there when we get to class. I'm sure Dr. York's videos also has other examples, so you could look there as well. Last, we're going to look at the squeeze theorem before I wrap this lecture up, so I'll see you in just a second. OK, so I'd like to wrap up now with an example of the squeeze theorem. I'm also going to go ahead and give you the statement of the squeeze theorem as well. So if f of x is less than or equal to, well, it is going to be less than or equal to f of x, but I need to put g of x here, giving myself another function. So g of x is less than or equal to h of x. So here I have 3 different functions, and they're ordered kind of like this. When x is near a, except possibly at a itself, and if the limit as x goes to a of the smallest function, I guess the one on the bottom, so limit as x goes to a of f of x equals the limit as x goes to a of h of x, and that equals some L, then the conclusion is the limit as x goes to a of g of x is also L. So we're going to dissect what this means in an example in just a second, but all you need to know is that there are these 3 functions ordered this way, and some little region about an x value we're interested in. If you can show that the 2 outer ones are forced to some value, like the same value, that basically squeezes the middle one into the same value. So it's a very specific situation, but we're going to see it used in this example. So we're going to show that the limit as x goes to 0 of x squared sine of 1 over x is 0. So that's what we're going to show. You may be tempted to use one of those very first limit laws I gave you because there's a multiplication, right? So you could plug in 0 to this function, multiply it, and plug it into this one. What's the problem, though, is if you try plugging in 0 here, this goes undefined. So you can't multiply a real number times something that's undefined. So we have to have some other thing to take care of this. One fact we do know from trig is that, so we know sine of any number is between -1 and 1. So a sine graph will always stay between -1 and 1. So this is our starting point. From here, what we're going to do is we're going to multiply through so that we can transform the middle of this inequality into what we're looking for. So what we're missing is x squared. So we're going to multiply everything across by x squared. So that's going to mean I get -x squared less than or equal to x squared sine 1 over x squared times x squared. So I can multiply across like this, and none of the signs change. That's because x squared is at least 0, if not positive. So that means none of the signs flip. Okay, so that's why I'm allowed to multiply through. If it's a positive quantity, you can do that. From here, what I'm going to do is I've got my lower function now. You could think of this as f of x. I've got my upper function. You could think of this one as h of x. So the limit as x goes to 0 of f of x, what is that? So this limit, if you plug in 0 for this polynomial expression here, you're just going to get 0. However, that's also equal to the limit as x goes to 0 of h of x, because that's what happens when you plug in 0 into this one. You get 0. Therefore, by the squeeze theorem, we can conclude that the one in the center, so this one is called g of x. This is the one in the center. So therefore, g of x, its limit as x goes to 0 equals 0. So that's really all there is to it. So you have to build up some kind of inequality. Usually you use, you find a function that can be bounded between two values. So a sine or a cosine might be a good indicator that you're about to use the squeeze theorem. You build it up like this. And then if this was like a free response or something like that, you would want to write a statement. You'd be like, hey, I used the squeeze theorem. Here's the two functions I squeezed it between. So if you're writing a free response question, make sure that's very clear. OK, I think I'll just show you a graph of what this looks like, just to give you a little more intuition of what happened. So the x squared graph looks like this. This was my h of x. Negative x squared, what do you do when you take the negative of a function? You flip it. So this one right here is my f of x, which is negative x squared. I see that I have gone off the screen a little bit, so let's put that right here. And we're saying that we've squeezed this function between these two functions. This is actually what this crazy function looks like, if you're curious. It's like this. So I'm going to draw it in blue. It kind of comes down like this, goes like this, and it starts oscillating like crazy in the middle. And then it starts oscillating, and then it goes back out again like that. So this blue one right here is the g of x we were interested in. So it stays between the two functions the whole time. It does some crazy stuff in the middle, oscillates like crazy, and then it goes back out again. But right here, we've forced all three of the functions to be 0 there, and we've sandwiched the blue one in between the two functions, h of x and g of x, or h of x and f of x. OK, I think I'll stop there. I will see you next lecture where we'll start talking about continuity.